one of the most extensive zones of destruction on planet Earth. Its most visible features are the hundreds of volcanoes that line the shores of the Pacific Ocean. They form an arc which extends 25,000 miles from South America along America's northwest coast to Alaska, and then down through Russia, Japan, and Southeast Asia, all the way to New Zealand. Cataclysmic eruptions have occurred here throughout history. August 1883, Indonesia. The Krakatoa volcano blew itself to pieces, creating the loudest sound in recorded history. June 1991, the Philippines. Mount Pinatubo blasted debris 22 miles into the atmosphere. Suffocating ash swamped over 2,500 square miles. And in May 1980, Mount St. Helens caused $1 billion of damage. The ever-present threat from these volcanoes makes it essential for scientists to understand the forces that power them. The investigation begins here, in Alaska. This land of rugged beauty marks the most northern extreme of the Ring of Fire. 75% of all the volcanoes in the United States are situated in Alaska, making it a perfect laboratory for volcanologists. The first step is to discover how the Ring of Fire's giant volcanoes form.
We're headed to Augustine Volcano, which lies in Cook Inlet, and it's part of the chain of volcanoes that extends all the way down into the Aleutian Islands.
It's a 60-mile journey out across the frigid Alaskan water. In the distance, the volcano soon appears.
There's the Augustine Volcano over there. It's a perfect day to visit.
From high above the clouds, Dr. Bull can gain a clear view of the volcano's distinctive outline. Augustine is a stratovolcano, the type of volcano found all around the Ring of Fire.
Stratovolcanoes are quite unique in that they are shaped as beautiful cones, and Augustine is a perfect example of that.
Augustine last exploded in January 2006, the most recent of 7 eruptions here since 1935. Over the years, solidified lava flows have gradually built up on the volcano's flanks. To investigate what makes these volcanoes so dangerous, Dr. Bull climbs high up on the side of one of these lava flows.
This lava is made up of blocks. There's bits that are a little denser than others, and you can see there's a lot of different pieces to it. So we call this a blocky lava flow.
This blocky lava provides a crucial clue as to why the Ring of Fire volcanoes can be so deadly.
This lava is more thick when it comes out of the volcano, and its thickness will have an effect on how it runs down the slope. The thickness or viscosity of lavas can be shown in a number of ways. Hawaii lavas are quite runny. Honey is a perfect example of that. If you have the volcano putting out Hawaii-like lava, it's going to run quite easily down the rock. Whereas if you have something more like these blocky lavas, they're going to be a little bit more like peanut butter. They'll still run, but the viscosity is much greater.
The viscosity of lava is primarily determined by the amount of silica it contains. Silica is the most abundant mineral in Earth's crust.
The more silica, the thicker or more viscous a lava is likely to be.
Hawaiian lava contains little silica, so it's runny and produces a relatively flat landscape. But Ring of Fire lavas are rich in silica, making them sticky and less able to flow, creating tall, cone-shaped stratovolcanoes. During the 2006 eruption of Augustine, thermal imaging cameras were used to study the volcano. They showed this sticky lava building up layer upon layer. But the thickness of this lava also makes these volcanoes lethal.
Because these volcanoes have lava that is thick, things don't move through them very well. And bubbles of gases can build up.
Deep in the earth, under immense pressure, molten rock called magma contains dissolved gas. But as this magma rises, the pressure decreases. This drop in pressure means bubbles of the gas begin to appear, just like opening a bottle of soda. If the magma is runny, these gases can safely escape. But in sticky, silica-rich Ring of Fire magma, the gases can get trapped, often with terrible consequences.
Like trying to have a bubble move through peanut butter, it won't happen quite so easily. So there's a lot of pressure that builds up. And once that pressure builds up, it reaches a point where it can't take all that pressure anymore.
The result? Giant explosions caused by the catastrophic buildup of gas inside the molten rock. This is the reason Ring of Fire volcanoes can be so dangerous. But it's not usually the initial explosion that kills. It's what happens next.
Those explosive eruptions can create plumes that go up for tens of miles.
When these plumes run out of energy, they can collapse back down the sides of the volcano in a superheated avalanche of ash and gas. With temperatures of 1,300 degrees Fahrenheit and speeds over 100 miles per hour, these flows destroy everything in their path. A terrifying consequence of the explosive eruptions caused by gases building up inside thick lava. In the next stage of her investigation, Dr. Bull searches for clues as to how this sticky lava forms. On Augustine's lower slopes, she hunts for lava samples from inside the volcano. This giant block of solidified sticky lava was once molten magma deep underground. It was blasted out here during an eruption, and it came with some intriguing evidence.
So what I'm seeing in this rock is a lot of minerals and a little bit, in some cases, of hornblende.
The presence of these hornblende crystals provides a crucial clue to how the magma formed.
This is important in telling us something about magma conditions where the hornblende crystallized. Hornblende is a mineral that only forms in the presence of water.
These hornblendes show water exists deep in the earth. Scientists suspect this water plays a crucial role in creating the magma that powers volcanoes. Deep underground, rocks are hot and semi-solid. It might seem that the presence of water would cool them down. But that's not what happens. This water, which is under huge pressure, alters the rock structure and causes them to melt, forming plumes of magma. This molten rock soars up to the surface, building giant volcanoes. Without water causing magma formation deep underground, these Ring of Fire volcanoes would simply not exist.
A lot of this process we're still working on and we don't understand, but there's a fair amount of it that we do. And water has a very significant role in when and how rocks melt.
The investigation into why the Ring of Fire is so dangerous has uncovered two important pieces of evidence. Blocky lava flows are evidence of thick, viscous magma which traps gases inside volcanoes, leading to explosive eruptions. And hornblende crystals reveal that water deep underground encourages the formation of the magma that powers the volcanoes. The geology detectives figure out how this water gets underground and make a remarkable discovery: the chemical signature of microscopic organisms inside the volcanoes. All around the Ring of Fire, explosive magma is forming deep underground, fueled by water. Solving the mystery of where this water comes from is the key to how scientists will figure out why the Ring of Fire is so dangerous. The investigation now turns to Mount Lassen, an active volcano in Northern California. Surrounding the volcano are bubbling hot springs, boiling mud, and volcanic vents called fumaroles, belching superheated steam and gas. All this thermal activity is driven by the immense heat rising from magma deep underground. By sampling the gas coming from these fumaroles, scientists hope to discover the source of the water which causes the magma to form.
This device measures temperature. The temperature of this fumarole is 92.5 degrees C, about 200 degrees Fahrenheit. So just about at the boiling point for this elevation. And that's what we want for a good gas sample, a good boiling fumarole. So you can see what's happening at the surface here, all the steam coming out of the ground, but it's the gases that are along with this steam that we look at closely. And the composition of those gases tell us about what's happening at various depths beneath the ground where we can't see.
Tests on these gases, collected from volcanoes all around the Pacific Ring of Fire, have revealed something surprising. The gases contain carbon-12, a type of carbon that comes from living organisms. The specific levels of C12 found here are the unique signature of tiny sea organisms called phytoplankton. Billions of phytoplankton live in the ocean. As they grow, they absorb carbon-12 into their cells. When they die, they fall to the bottom, forming layers of sediment. In this way, their carbon-12 is transferred to the seafloor. Intriguingly, scientists have found this same carbon-12 pouring out of volcanoes all around the Ring of Fire.
Volcanoes of the Cascade Range have carbon dioxide that's very rich in carbon-12, and it's almost like you're cooking oceanic sediments that are rich in phytoplankton down deep beneath these volcanoes to generate the carbon dioxide you see coming out the top. That links this carbon dioxide to organic sediments way offshore in the ocean. The organic matter that was originally phytoplankton becomes carbon dioxide that we see at the surface.
Seafloor sediments are getting into volcanoes, and these sediments contain seawater. This is the water that causes the rocks to melt below the volcanoes, forming magma. But a mystery remains. The magma plumes feeding the volcanoes lie sometimes hundreds of miles from the ocean. The scientists now have to figure out how the sediments loaded with seawater are moving so far inland. To find out, the investigation heads for Alaska's Chugach Mountains. The research here begins with an analysis of the local rocks.
Oh, this is a really neat boulder that's right here. And what you can see in it is that there's this whole mixture of rock types. You can see that there's this black stuff, which would originally have been mud. There's several different colors of kind of greenish rocks, which would be kind of different flavors of volcanics. So here it looks like there's limestone, And I'm going to put some acid here, and if it fizzes, it's limestone. Yep, sure enough, that's what it is. And this would have formed in the ocean. And so this is made up of the bodies of little critters. It got incorporated into this rock, and now it's up here in the Chugach Mountain.
The presence of jumbled oceanic rocks 20 miles from the sea is evidence that something remarkable is happening at the bottom of the ocean.
The fact that you have this mixture of rock types here is evidence for the seafloor moving.
Geologists know that only an enormous process called subduction could shift these mixed ocean sediments here. Subduction occurs when the seafloor moves and slides down under the land. As it descends, the top sediment layers are scraped off by the land like a snowplow scoops up snow. They're pushed up into a huge mound of mixed-up rocks. The Chugach Mountains were formed in this way. The seafloor, loaded with water, now continues down into the earth. This is how seawater gets deep underground, where it creates the magma plumes that build the Ring of Fire's explosive volcanoes.
Where we're at right now, the Pacific is subducting beneath us to the northwest. At this northern part of the Ring of Fire, it's about 20 miles beneath our feet right here. But if we were to go off that way where the volcanoes are, it's about 60 miles beneath our feet there. And so as it goes to the northwest, it subducts and then brings water and sediment into the earth. That ends up causing melting in the mantle, and then that melt rises as magma to volcanoes.
The investigation to discover how water is getting down below Ring of Fire volcanoes has turned up intriguing clues. Carbon-12 samples indicating that ocean sediments are getting deep below the Ring of Fire's volcanoes. And mixed rocks in the Chugach Mountains, 20 miles inland from the ocean, are evidence that the whole seafloor is on the move, sliding deep under the land. This process is the engine that powers the Ring of Fire's killer volcanoes. But deep underground, the Ring of Fire hides another, even more deadly secret. Earthquakes that can destroy entire cities. The Ring of Fire, a lethal line of volcanoes. 75% of all the volcanoes on the planet. These fiery peaks encircling the Pacific Ocean are built by tremendous forces deep in the earth. Eruptions here have taken many thousands of lives and destroyed billions of dollars of property. But an even bigger killer is present on the Ring of Fire. Earthquakes. 90% of the world's quakes occur in this narrow band around the Pacific, often with disastrous results. Sumatra, September 2009. A giant earthquake left more than 1,000 people dead. Mexico, September 1985. More than 9,000 people were killed by a massive magnitude 8 quake that shook Mexico City. And Alaska, March 1964. North America's greatest ever recorded earthquake near Anchorage. This quake was so powerful, ground movements were observed 4,000 miles away in Florida. Such awesome power drives scientists on to discover why these deadly quakes occur all around the Ring of Fire. The investigation moves to Prince William Sound, 36 miles from the epicenter of the 1964 Alaskan disaster.
We're at the northern edge of the Ring of Fire, and we're going to be looking at evidence for how geologically active this area is today.
Heusler heads for Montague Island, a place that's permanently scarred by the powerful forces which shape this entire region. On land, he finds a rugged, boulder-strewn shoreline.
So you can see we're at the edge of the ocean. We're in a high energy environment. There's boulders all over the place. And we're at the top of the beach. Waves have been crashing here and basically getting rid of the little tiny rocks, leaving only boulders behind. And then right here you can see that these boulders are kind of lined up against each other like dominoes. And so it takes big waves to flip these over and line them up kind of like dominoes like that right here.
But it's not this rocky beach that reveals how violent Ring of Fire quakes can be. The real evidence lies 1/4 of a mile inland. Heusler hunts through the thick undergrowth. Hidden by the trees is a near identical line of boulders.
We've hiked in, thrashed through the alders, the Alaskan jungle up to here. We're probably 25 or 30 feet above sea level at this point. And what we have here is a beach. I mean, this is basically a perfectly preserved, high-energy beach environment like we were looking at down on the shoreline. And you can see here, once again, there's these big boulders that are sort of laid over in this domino-like fashion, sort of pointing uphill as a result of this big waves pounding on the beach, flipping the boulders over, pointing in the uphill direction.
This inland raised shoreline runs for hundreds of yards, parallel with the ocean. It's a key piece of evidence, and it can only mean one thing. The land itself must have recently risen up out of the ocean, taking the entire shoreline with it.
It means that there was an event that was essentially an instant in which this region was uplifted to this elevation and made this here. This has to have been a result of a big earthquake. Really cool. What we're looking at here is a result of the 1964 Great Alaska Earthquake. Pretty much right here where we're at is where there was the largest uplift that occurred.
The massive earthquake here not only lifted the land out of the sea, it also caused a wave of destruction, devastating nearby anchorage.
It was a magnitude 9.2. It was the second largest earthquake ever recorded on Earth. It was just enormous. It lasted 4.5 minutes of ground shaking.
What happened throughout this region offers evidence of the type of quake that makes the Ring of Fire so dangerous.
So we know from this kind of earthquake that occurred here in 1964 that this was a thrust-type earthquake, or even there was a fancy term, megathrust earthquake, because it was so big that occurred right here. And this is a result of the slippage of one piece of rock over another, or one underneath the other.
Megathrust quakes like this are the most powerful on Earth and are one of the great dangers of the Ring of Fire. If they occur under the ocean, they can generate killer waves called tsunamis. The Great Alaskan Earthquake of 1964 caused a tsunami over 200 feet high. Waves traveled over 1,700 miles, claiming lives as far away as California. But this disaster was nothing compared to what happened in 2004. On December 26th, tragedy struck when an enormous underwater megathrust earthquake off the Asian coast generated monster waves. The coastlines of 14 countries were swamped, killing more than 200,000 people. The vast scale of this disaster was a brutal indication of the power of megathrust earthquakes. It's given urgency to finding out why these quakes happen all around the Ring of Fire. Once again, the Alaskan landscape is the perfect geological laboratory.
So we're headed to a seismic station in south central Alaska near the tip of the Kenai Peninsula.
Millions of years of the Ring of Fire's volcanic activity and rippling earthquakes have given Alaska an incredibly rugged landscape. It's not easy to find a flat spot to land.
Clear on my side.
High on the hillside lies West Seismic Station, protected under the yellow cover from the elements and the local bears.
So this is the vault where one of our seismic stations lives. This is one of the many seismic stations that dot the state of Alaska.
Several thousand seismic stations like this exist, all the way from Alaska down to California.
This whole system together monitors any kind of seismic activity, any sort of earthquakes throughout this whole area. It's part of a whole network on all of the volcanoes around here, on the mainland, and throughout this whole area. So the seismic data can be used not only to judge the severity of the earthquake or the magnitude, but also when taken across a number of stations to pinpoint the location of that earthquake.